Um, Let me just make sure that the recording is working correctly. It's a bit, the level is a bit high. So, one, two, three, testing. 1, 2, 3, testing. Well, hopefully it's okay now. Yeah, you may have noticed that I have re-recorded several of the recordings because the sound was not okay, and yeah. So, news first. All the materials for this week are available in the lesson plan. So, you have the tutorial for the next week. You have problem set 1, whose deadline I think it is September 8th. All right, at midnight, remember you will be penalized a certain amount per hour, right? Read the instructions. I can't remember what that amount is. A certain amount of, I think 2% per hour, right? Of the score for 50 hours after the deadline, after which you're not allowed to submit at all. Okay, so yeah, and tomorrow we're going to have the first tutorial, and the handout is uploaded since last week. Unfortunately, we haven't quite covered the part that is covered in the tutorial in the lecture, right? I have uploaded a recording on Monday, maybe, well, hopefully as many as you, of you as possible have gone through that, right? But nevertheless, we're going to repeat that part right now so that we make sure that everybody has gone through it. And it's going to be covered tomorrow in the tutorial as well. So this part was about assembly languages. You should be familiarized to a certain extent with it if you have taken computer organization. How many of you have taken computer organization, by the way? Well, so there are people who haven't taken computer organization yet. They hear about this for the first time. Okay, so most of you have taken computer organization, so you should know in principle what it is. So it's just a means of making machine language more readable. What's machine language? Numbers, right? So bytes represented as numbers, usually written in hex. And when you see something like 0xC9, you have no idea what the processor might be doing with that, right? The way to make it easier is to give a name to that number, right, in the form of a mnemonic, and that becomes an assembly language instruction. Then, you know, the assembly languages have evolved in the way of allowing for symbolic names to be used instead of direct numbers. So you can have some notion of variables. You can define references in memory by symbols, and the addresses of those symbols would be figured out automatically by the assembler and so on. However, the power of the assembly language unit, which is the instruction, is very limited, right? Is much lower than the power of a line of high-level language. There's no structured programming. So programs tend to be large in terms of lines of code, but rather small in terms of, you know, executable size. So you may write a program that has 20,000 lines of assembly line code, which is large. It's a large project by the standard by which programmers' effort is measured, right? But those 20,000 lines of assembly language code may generate only 50K of executable code, right? Which is a very small program in terms of executable sizes nowadays, right? Most programs would be at least a few megs. So this goes to show the limited power of the assembly language. You write a lot, but you produce very little executable code. It's different for every architecture, so the Pentium would have a different assembly language as compared to the MIPS, which is probably what you have seen if you have taken computer organization. So, because of that, then because it is no point in burdening you with details, what we want to understand about assembly language is what kind of skill does a programmer need to be effective at that level, right? So we're going to restrict C in such a way that you get to experience that level of skill, right? Programming in this restriction of C will take as much skill as if you were programming in any assembly language program, right? We're going to limit the power of the instructions. So you get to write a lot more code for achieving the same thing. We're not really interested in architecture, right? So we're interested in how do we view an architecture, a generic architecture through perspective of programming language. So we call this the vanilla assembly language. It's actually C. You're going to write a program that can be compiled by a C compiler. We're going to allow, as I was saying, so it's very limited. We're going to allow only 6 global variables, which we call by these names. Incidentally, these are the names of the Pentium registers. Actually, there's 8. I'm going to introduce 2 more later when we talk about procedures. For the time being, we only use 6. We simulate the memory by this unsigned character array, which we call M, and the number of elements has to be sufficiently large. It doesn't quite matter how many of them, right? So we don't want to take too much memory from the system unnecessarily. We're going to limit it to 10,000. But 10,000 is just an arbitrary limit. No local variables. So you're not allowed to use any local variables. One single function, right? And this is because C is like that. You have to put your code in a function. That function is just a placeholder, does not have any specific role from the perspective of assembly language. And we're going to call that function exec, and it's going to take no arguments and return no result. All right, so global variables simulate registers. The array simulates memory. That's placeholder for code. And then we have to discuss the elements of the language. And we start with discussing the operands. So an operand can be, any global variable can be an operand, right? Then we have what we call index expressions, which are the kind of expressions that we can give as indices to the array M. And these would be a global variable, a constant, which should be an integer, of course, or the sum or difference of the two. Global variable plus constant, global variable minus constant. You're not allowed global variable plus global variable minus global variable star global variable, right? So you're restricted syntactically to only these 4 forms. Then we have array references, which are simulating memory references. So M indexed by an index expression, right? And this would access 1 byte of the array. Remember, it's unsigned character. But we may want to access in memory data of various sizes. So, for instance, if we want to access 4 bytes that we would coalesce into an integer, right? We should use something like this form, right? This one. Oops. This one, right? Which takes the address of M, converts it to a pointer to integer, right? And then indexes it by this expression. But when we apply the index, it takes the array element, right? So M index expression takes its address, converts it to pointer of type integer, and then when we dereference it, instead of accessing just 1 byte, we access 4 bytes, right? And this is because of a peculiarity of the Pentium where memory is byte indexed, right? So every address will give you back 1 byte. If you want to access 1 integer, you have to access 4 consecutive addresses. So this is exactly what's happening with this expression. And similarly for data of other types, if you want to access an unsigned integer, we apply the same trick, right? We take the element, we take its address, we convert it to a type pointer to unsigned integer and then dereference it, right? So it's a bit silly because we're saying star, essentially, address of something. These two cancel each other, right? So it seems like they cancel each other, but it's not quite true. Because in the process of doing that, the pointer has been converted from pointer to one type into a pointer to a different type, and then there's a different number of array elements that are accessed simultaneously through this expression, okay? And there's no other way to do it. So we want to access possibly data of different sizes, shorts and unsigned shorts. So let's look at examples of operands, right? We're going to have operators later, operators and operands, right? So register operand is EBX, for example, a global variable. Integer in memory will have this format, right? Is the integer indexed by the register ESI. The short number indexed by EDI plus 4. So EDI plus 4 is converted, it represents an address in memory, so we are dereferencing that pointer. ECX minus 1 byte, ECX is a pointer, right? We want to decrement that pointer and access the memory element, and so on and so forth, right? Notice that several are not allowed, so let's go very quickly through the summary. This simulates Pentium operands, right? So somebody asked in the comments to the blog, this is a constant, right? If we have a label, the label is a symbolic constant. The address of a label is a symbolic constant. It's not a variable. Because of that, it doesn't need to be declared, and it doesn't need to be declared before it is used. I can use it and then declare it later, or put it in the code as a target later. All right, and the compiler will figure out what the value of this is, but it is a constant because the value of that expression never changes throughout the running of the program. The target of an instruction, the instruction doesn't move around, right? So the target of an instruction, the instruction stays in the same place in memory, the target of an instruction doesn't change, therefore that expression is a constant. All right, so we need to be explicit in forming 4-byte entities, and we discussed these examples, and none of these are allowed, right? So two global variables in the index expression not allowed, the multiplication is not allowed, EAX star EBX is not allowed, right, because is of none of these forms, right? So it's not a global variable, it's not an array. It is an array reference, but not of, with the index not of this time. Oh no, it's not an array reference. So it's not of any of these times. And star, int star EAX, again it was a discussion in the forum. This is not allowed. EAX should always be an integer. Can't convert it to a pointer. Okay, code. So we discussed operands. Operands are building blocks of the language. So now, for code, we have assignments, and assignments are restricted to this format. Operand equals operand, operand plus equal operand, operand minus equal operand, and we use all these shortcut operations that treat the destination of the result as one of the sources, right? Typically, an operation is between three entities, right? Two sources and a destination, two operands and a result, right? But we force one of the results to be the same as the, or one of the destination, or one of the sources to be the same as the result. Okay? So all the shortcut assignment operations are allowed. Bitwise conjunction, bitwise disjunction, bitwise exclusive OR, modulus, right? As long as it's in the form operator equals, and it only takes two operands, the entire assignment. So these are legal examples, right? So anything like this is legal, and these would be illegal, right? Illegal because here on the right hand side we have yet another operator, right? If you write If you write EAX equals EAX plus ECX, that's fine, right? Because it effectively means EAX plus equals ECX. But if you use three different addresses, it's a three address instruction, this one, right? Then that's not allowed. Also, this is not allowed as an index expression. And two memory references are not allowed, right? So this is the first rule that we have here, no two memory references in the instruction. Right, so we are very restricted in the power of our instructions. The other type of code is the goto statement, which can be a static goto, go to a label, or go to star operand, a computed goto, right? And the operand's value must be of this form, as we discussed last time. Then we have Boolean expressions, and again, all the Boolean expressions must have two operands, and no two memory operands are allowed in the same expression. Okay? So a single operator and two operands on the sides. So you can have EBX less than ECX, or EBX less than memory of 3. These are legal, but nothing else. And then we have if statements, and notice that if statements are restricted to a single branch, which needs to be a single goto instruction. That's all. Okay? So if Boolean expression go to somewhere, that's all that is allowed. So any questions so far? Okay, so let's see how we can write some code. So this is the original power function, of which there was much discussion in the forum. Remember, this function, it's not that important what it does. It's important, it was introduced as a means to showcase elements of C, and it's used right now to showcase a systematic translation scheme. That's all, right? How it works is much less important. So a lot of you went into what the bitwise is doing and why the bitwise is so complicated. Right? So one thing you could do is try to debug it and see how it works if it's such a mystery. But nevertheless, what we want to understand here is a syntactic translation scheme. We wanted to showcase the fact that any program can be easily translated into something that looks like an assembly language program. So let's look on the right and recognize all the elements of the assembly language. So we have declared the limited global variables that we're out to declare, and we're writing this function, exec, and this function has to have some arguments and return a result. And for that, we always make a convention. The convention is always up to you. If you're answering an exam question or a homework question, you will have to say, I want arguments A and B to be implemented as registers ECX and EDX. So it's up to you to make a choice there. You can put them in memory somewhere, you can pick registers, whatever. And you want to return the value somewhere. So whatever is returned here will be available in register EAX upon return from this procedure. Okay? So then what do we do next? All right, so this is the first thing. It's a convention. I'm telling you just beforehand, so this is something we've seen before. A return statement, a label, must point to some statement, right, just to clear the confusion about, potential confusion about this. I can't put a label just before a closed bracket. So if the label comes at the end of a block, we have to create an empty block to make the label point to it. All right, so one good scheme is to implement variables which are local in this case in the program as registers. So we're going to represent S by the register EAX and CNT by the register EBX. All right, and it's convenient because to pick EAX because at the end we're going to return S, and our convention is that the results should be available in the register EAX. So naturally, when we reach the final point of the program, we will have the result available exactly where we want it. So then we translate as if, it's pretty much a one-to-one translation, right? So the next thing is, if b less than 0, return 0, right? So if EDX less than 0, this is the equivalent of b, right? So now we can't return, we can't put the code there. We can't put the then branch of the if statement right there. We have to create a goes-to statement that goes to a label that executes the then branch, right? So this part of the code has to be shifted somewhere else, which becomes the target of the go-to statement that is inside the if. Okay? But this can be done all the time. So what we're going to do here at return 0, we're going to load EAX with 0 as we are expected, and then we have reached the end of the function and the result is correct. Next is we want to translate the while loop, and for the while loop we have a systematic translation scheme. So you see, we're going to look at the loop's body first, which is the if statement. So the if statement, right, looks like a skeleton. There's an if, and there's a placeholder for the then branch, and a placeholder for the else branch. And we can take this skeleton and convert it into a corresponding skeleton of the vanilla assembly language. So what are we going to do here? Well, I am going to negate to compute this result. Alright, so I'm going to compute this result, and this is done by these two instructions. So you see, I can't be changing the value of b. And in order to perform the computation, all these instructions have the destination being one of the sources. So the easy thing that we want to do is transfer, or save if you want, save the value of b into some temporary register and perform the computation with that temporary register, so the original value is left unchanged. So you see what I do here. We load EDI, which is the temporary cache, with the value of b, and then we perform this computation, right? And this is effectively the result of the Boolean expression here, right? 1 shifted by 30 bits is exactly 0x400000, right? So we have replaced this expression, whose result is always a constant, by its constant value, which is here. And then we perform the bitwise AND, and then the result of the Boolean expression is in register EDI. So we're going to say if EDI, exactly if whatever the result of this expression is not 0, right? So if EDI is not 0, go to then branch. Again, we can't put the code of the then branch right there. We have to create a label that points to the code for then and relegate all the code there. So then, right, this is going to be the code for the then branch. And what happens if this is 0? Then we're going to stay here, and this is going to be the code for the else branch. So in effect, right, we have this, right? We have to translate the then branch here into vanilla assembly code and put it in the correct placeholder of the skeleton of the vanilla assembly language, right? So if you look carefully, this skeleton, which is the yellow stuff, has left 2 holes, one here and another one here, and we want to fill those holes with a translation of the then branch and the translation of the else branch, right? So we are going to take the then branch, convert it into vanilla assembly language, and place the code here, right? And it's quite straightforward. So the problem here is that we can't quite use this expression directly. we have to do it in several steps because we have more than one operator there, right? We have two multiplications. So what we do is we square EAX, which represents S. So we do S times S, we square EAX, and then we multiply EAX by ECX, and we have achieved the effect of the first assignment. Okay? What about the second one? Well, again, this thing is a constant. It is an expression, but its result is always the same. So I'm going to replace that constant by its value here, right? Yeah. Then I'm going to perform B, bitwise AND, this value, which is what happens in the first assignment, and then what is left is the shift left operation, which is performed here. So first we perform EDX bitwise AND whatever value is there, and then we shift it by 1 bit. Is this clear? Is this clear? All right. And the else has to be translated and placed into the placeholder of the else branch. Right? So this one is much simpler because we square S, and this is a direct translation, and then we shift B by 1 bit, and again this is a direct translation. So we have converted the if statement. All right? With both the then and the else branch. Is this clear so far? Take 30 seconds to mull it over. Pay attention to the fact that this is systematic. The if is a skeleton. I have a skeleton for the if in the high-level language, which converts into a skeleton of the if into the vanilla assembly language. The placeholders that I have in the high-level language if correspond to the placeholders that I have in the vanilla assembly language. And then what I have to do is recursively perform another translation for the placeholders. And the skeleton, the yellow skeleton, works irrespective of the instructions that are in the then branch and in the else branch. Is this clear? Okay, so let's look at the while. So the while works by the same principle. The green blob is a skeleton. It has a placeholder in the middle, right, between the open brace and the closed brace. That can be anything I want, right? What I want to focus on is translating the green blob on the left into the green blob on the right. Okay? So what we're going to do is perform this test, right? So remember, EBX is CNT. So we decrement EBX, we test EBX, and here we negate the condition. So the condition is greater or equal. On the right-hand side, we negate it, we say less than. If this condition is true, which is the negation of this one, I should not be executing the loop. So I'm going to jump to a target that takes me outside of the loop. Otherwise, I should continue on and keep executing the loop. Whatever translation of the blob on the left I have, I'm going to execute it on the right. And then at the end, I'm going to repeat. Right? When I reach the bottom of the loop, I perform a go to, and I go back to the top, and I do the test again. And if the test is true, which is the false of the other guy, I exit the loop. Right? So again, pay attention that it doesn't matter what I have inside the while loop. Right? I perform the translation of the while skeleton. I go from left to right in the green blob. And then I have a placeholder inside the green blob on the left. And I translate that and put it in the blob, in the placeholder of the green blob on the right. and it's systematic. All right? Is this clear? So this is going to be very important when we further discuss the semantics of languages. Okay? And we're going to practice this to a certain extent in the next tutorials. Any questions? Some of you are still squinting, so I'm waiting for the squinting to stop, which means that probably you either resigned to thinking that it's too complicated or actually understood it. Okay, can we move on? Okay, how do we test the code? Well, we're going to write a C function. So at this point, we can take it easy, right? No restrictions. So the important thing is that you call exec, right? And you set up the parameters. But sometimes the arguments to the function, the input to the function can be quite complicated. I may say sort an array of random size placed at a random address, right? So the code that you can use here is any C code, as long as it only sets up the inputs. Remember that the main procedure is not part of your answer to an exam question. Only the exec is, right? In your homework, you're allowed to use anything that will allow you to test your code thoroughly. Right, as long as you want to do any C code that will allow you to test your code thoroughly, right? I don't care, but don't do any of the computation that exec is supposed to do inside main, because that will be you know, the wrong thing to do. So this is what we do, right? We set up the arguments, we call exec, and then we print EAX because this is what we are expecting. This is what we're expecting the result. All right, and the same here. And we can have as many tests as we want. And somebody asked, why do I have this here? Well, in many IDEs, if you run your program and the program is not interactive, you see very quickly a black window showing up and disappearing. Right? Because those IDEs are expecting that your program will be interactive, will open a window, you will perform some interaction, and then you will close that window. So what I'm doing here is I'm forcing the program to wait so I can look at the output. Right? It doesn't have any intelligent role. It's the easiest thing to do. I could put the pop-up window and say press OK when finished viewing or something like that, but too much effort for that, right? So getchar is sufficient. And obviously, in your exam answer or in your homework submission, you don't have to do it, right? It's not absolutely necessary. So most likely, when I'm testing your programs, I will be using command line tools, or whoever is marking it. I was going to use command line tools, so not that much of an issue. All right, so set up arguments, perform computation, print results to verify correctness, right? Remember, no computation allowed in the main program. If you're writing an exec that does nothing, and then you're seeing printf power of ECXEDX, where power is the library function, obviously that will earn no marks. Okay? All right. So remember, all software in the end executes machine code, right? That's what happens. We often abstract that away. We appear oblivious to the fact that you know, in our daily life as software developers, we tend to forget the fact that in the end, what is executed is machine code, right? So we want to create that awareness, because that will give you a hint on various ways, how various ways of writing a program can affect performance in terms of speed and memory consumption, right? C was devised as a portable assembly language. Remember that. So this is trying to yet again emphasize that. So right tool for the right purpose. If you hear criticism that C is not a good language to create a GUI, fine, that doesn't mean C is useless. Okay, so it is important to understand the relationship of C to assembly language as well as C to other languages. C is sort of the middle ground, right? Most compilers and interpreters are written in C. And they're not written in assembly language directly anymore. They used to be 40, 50 years ago, right? But they've been replaced by C because of this, okay? And hopefully I've given you more insight in what we mean by translation schemes. And we're going to do even more of that when we talk about semantics and we talk about the meaning of programs. I would like to re-emphasize at that point that in the end, the meaning of the program is the machine code that the program is executing, right? So hopefully this will help a lot. So this is it for last time's lecture, okay? And let's move on to today's lecture, which is about languages, grammars, and regular expressions. Okay? Before that, last chance. Any questions about the previous set of slides? Boy, I must be doing a great job, right? No doubts. Excellent. So, this lesson, we're talking about how to define languages, right? And we're going to see that the mechanism for that is called grammars, which is not surprising, right? You've learned, most of you, I think, would probably be speaking at least 2 languages. And the second language that you've learned, you were made aware explicitly that you have to learn about grammar, right? So, programming languages are following along in the same track. They would use a concept called grammar for specification. And we're going to want to see whether where grammars can be used as language generators. All right? And the typical concepts here are derivations, analysis, and language structure. Then we're going to focus on a narrower class of languages called regular languages, right? So it's narrower than general grammars. We're going to go back to general grammars next time when we talk about syntactic analysis. But for today, we're going to look at regular grammars, deterministic finite automata as an acceptor of regular languages, regular expressions, which is one interesting thing that may be useful not just for programming language work. And we're going to showcase the use of regular expressions in the language Ruby, which is the only one that has, one of the few, but the only one that I mentioned in the first lecture that has regular expressions as first-class objects. And we're going to understand what first-class objects are as well. So, what's a language? A language is made up of symbols, and symbols are elements of an alphabet. So we start with a set, finite set, which we call alphabet, contains symbols, and with these symbols we can create strings. Some of the strings are in the language of interest, some are not, right? So a language is a set of strings over that alphabet. So the easiest way to specify is just to enumerate the elements in this fashion, right? So this would be a language that has 5 elements. Obviously not very interesting, right? But possible. We can enumerate even infinite sets because if we have some sort of a rule, we can see what are the elements that come next. So this would be the language of positive numbers. Digits from 0 to 1, then I use a 1, followed by a digit from 0 to 1, then I use a 2, and so on and so forth. And I can create digits, numbers of any length. And the language of C programs. And You could think of enumerating all the C programs. That would be a very stupid idea, but you know, as a first approximation of how to generate a language, could possibly come to your mind. All right, so you start with the first program and next, and because C has a finite number of symbols, you could conceivably think of how to enumerate all possible correct programs, right? But would not give you an insight of how to write programs later, right? What are the rules of the language? So we want something that is more systematic. So enumeration, not a good way. It has to be finitary. So we have to, we should not be using ... right? That's what we mean by finitary. And we've been using ... quite a bit in the previous line. It should provide an efficient way of deciding whether a string belongs to the language or not, right? So I've enumerated the language, let's say, or I have this specification, but my problem typically is I have written a language, I give it to the compiler, first thing it should do is tell me whether, or decide whether that text that I have input is a correct program or not, and then proceed to translate. But the first thing that it should do is check whether the program is correct. It's part of the language. And also we want a bit more. We want to capture the structure of the language so we can perform some analysis and help along with translation. And we're going to see how that works in a minute. For instance, we have the concept of associativity, right, and precedence. If we say A plus B times C should somehow, right, the language should capture the fact that B times C should be performed first, and then the addition should be performed later. And all this is possible with grammars. So let's see what they are. So you should know that it comes from theoretical computer science, right? That part of theoretical computer science called formal languages. It's a language generator, essentially. So it tells us how to generate strings from the language. Next time, we'll see how we can convert the grammar into a mechanism for accepting, right? So we have two different problems here. Generating elements of the language, right, which is give me one possible language or give me many possible languages, right, generate. And the other is, which is more important for our purpose, accept. Take a input string and tell me whether it's part of the language or not. So we'll see how a grammar can be converted into an acceptor. And we're going to take the practitioner's approach, introduce concepts step by step, right? We're not going to be very formal. So the first thing that we need to learn about is production rules. Production rules are, constructs of this form, right? We have on the left a letter, and on the right a string of letters, and we put an arrow between the left-hand side and the right-hand side with the meaning of rewrite. So the first rule says E rewrites as bracket E bracket. The second rule says E rewrites as E plus E. And you're probably sort of guessing already that this generates arithmetic expressions with binary operators. All right? So this is what we call a production rule. And all of these are production rules, is a set of production rules. It's going to come in handy later, the fact that the awareness of this being a set of production rules. We have a left-hand side and a right-hand side, and the meaning is rewrite the left-hand side as the right-hand side. We have several kinds of symbols. The ones that are capitalized are called non-terminals. They cannot be part of the generated string. That's why. The other ones are called terminals because they can be part of the generated string. All right, and the important thing that we can do with production rules is perform derivations. We start from one of the non-terminals. For the time being, let's just call it one of the non-terminals, and we rewrite it according to a production rule that has that non-terminal on the left-hand side, right? So we can pick some rule. Let's say the third one, so E rewrites as E times E. And then I can take the first E. This is called a sentential form. We're going to see this later. This is called a sentential form, and I can pick some of the non-terminals in the sentential form and rewrite it further. All right? So the current sentential form is this. I pick one non-terminal and I rewrite it, right? The yellow blob will tell you what has been rewritten. The pink blob will signifies copying, right? So the rest of the sentential form remains the same. And this goes further and further, and you can pick you can pick in fact any non-terminal. Here we are making the conscious choice of picking the leftmost, and we'll see that we have leftmost derivations, rightmost derivations, and arbitrary derivations, and leftmost and rightmost have some sort of an importance at the later point, right? Not right now, not so important. But we continue the process, right? We pick a non-terminal from the current sentential form and we rewrite it, and this keeps going, and going, and going, and going, and going, and I think it's done, right? So the last sentential form is 1 plus 1, 0 times 1 in brackets, and it's an expression over binary numbers, right? And we have generated it in a sort of arbitrary fashion by just picking production rules at random. Okay? Now, of course, we don't want to just start on some non-terminal and see what we get, right? What's our luck today? What kind of expression are we going to get today, right? So this is just an example of a derivation. Keep it in mind. It's going to be useful later. Okay? And let's learn more stuff, right? So this expression, 1 plus 1, 0, brackets, times 1, belongs in the language of the non-terminal E. And this is the notation that we use, right? This curly L represents the language of the specifier, which is the non-terminal E. And we're going to see several other specifiers later, and we're going to use the same notation, language of something. This is the language generated by E. Is this clear? And of course, all the strings that we can generate using these production rules, starting from E, will be the language generated by E. Okay? All right. So that's what I just said. It's strange. You know, I made this slides last week, and now I actually don't remember what's going to come on the next slide. So I'm saying stuff, and then I'm realizing suddenly that it's right there. I should not have drawn it, but rather move on to the next view and have it there. All right. So similarly, 1001 belongs to the language of D, and it's very easy to construct a derivation that does that, right? So you figure it out how to do it. So now the formal definition that you would see in mathematics of a grammar is the following. We have an alphabet of terminal symbols. We have an alphabet of non-terminal symbols. We have a set of production rules, which is what you have seen on the previous slide. And we have a start non-terminal. We distinguish one of the non-terminal as the start non-terminal, right? And the language of that grammar is in fact the language of S. And this definition looks very cryptic. I'm just putting in there so it's for your general culture. But it doesn't say a lot of new stuff, because in practice, we're just going to use the rules, right? We're going to take the rules, and we're going to look at all the terminal symbols, and that's our alphabet, right? So the rules already tell us the alphabet. Why should I bother to have but mathematicians like to be very precise, right? So they would fix a sigma. Then I can take all the non-terminal symbols and put them in a set and call that the set of non-terminal symbols. And I can take all the rules and put them in the set of rules, pi. And then I can distinguish one start non-terminal, which is typically the non-terminal on the left-hand side of the first rule. And there I am having a grammar, right? This is the grammar. So once I have distinguished the start non-terminal, the language of this grammar is essentially the language of the start non-terminal, which we have defined the language of a non-terminal on the previous slide, right? But the grammar says, well, I'm distinguishing one, and I'm only allowing derivations of that one, right? Now notice that in the production rules we use recursion, all right? And in fact, recursion in grammars will bring all the problems that recursion has in general, right? Potential non-termination, ambiguity, and we're going to want to restrict recursion in some ways to make the grammar more well-behaved. Now, an easier way to deal with derivations is via the concept of derivation tree. Okay? So instead of looking at the derivation as a sequence of strings, we can look at it as a tree. So I start from a non-terminal, and when I rewrite that non-terminal, I make the right-hand side, each symbol of the right-hand side, I make it into a child in a tree. All right? So you can see E times E. So here I have E times E. And then I continue the process. I can pick another non-terminal and expand it, rewrite it, right? And yet another one, I pick this one and I use the rule E plus E. And you see at all times, we have this concept of a frontier, which is read from left to right and represents the sentential form that you have seen in the previous derivation when we looked at the derivation as a sequence of strings. Right? In the previous one, we've seen string, arrow, string, arrow, string, arrow. Okay? So here, that string will actually be on the frontier of the tree. So we can do it further by applying production rules, and at the end we're going to get a frontier that contains only terminals, and that is an element of the language. That is a string of the language. Right? Notice that in the process of building the tree, I'm also showing the part that is matched already, and this is something that language acceptors do. They try to match as much of the input string as possible. So when they recognize, they will try to build a derivation. Let me go back to the beginning. They will try to build a derivation tree for this string. They will be given this string in advance, and the question is, does it belong in the language of E or not? Right? So the language acceptor will try to build a derivation tree internally, right? And at all times, if possible, to match as much of the string as possible. And then it will use this, the first unmatched symbol, to predict the rule that needs to be applied next. Okay? So, right, or not just the first several, maybe. Right? So now here you can see that a plus is coming very soon in the input, so probably this rule should be used. Right? So that rule will be used, right? And then between the plus and the first unmatched part of the string up to the plus is just a digit, so probably one of these rules has to be used, right? So we use it, and then we match a bit more, and then we use again the first unmatched part of the prefix of the unmatched part, a certain number of symbols, to try to predict the next rule. This will make what we call parsing later more efficient, right? So we want to pay attention to this. The fact that we are able to match, as we proceed with our derivation, as much of the input string as possible on the sentential form. Okay, is this clear? All right. Now, how useful is this tree? It's which is I think the same, right? The same as here. How useful is this tree? Well, it definitely tells us that the string of interest belongs to the language, but how helpful would it be in translating the expression into, say, machine code, which is what a compiler does? Or how helpful would it be in interpreting the value and finding out the value of the expression, which is what an interpreter would do, right? And it's not that helpful. We would like to get rid of some of the garbage. So there's a lot of structure in it, but at this point, the non-terminals do not offer any information. The non-terminals alone are redundant, useless. So what we want to do is hoist the terminals to their parents or ancestors, right, and delete the ancestors somehow, or shortcut the ancestors in a way, so that we remove the clutter. Okay, and this can be done in a systematic manner, but in a systematic manner that is individual to every grammar. So when you see the grammar, you will have some guidelines, right? And there will be many customized rules, right? But generally, this is what I want to do. Especially, for instance, if I have a single child for a non-terminal, this terminal is useless. I can just shortcut this guy, right? And we can do this in several steps. So if the node has only one child, shortcut the node. If the node has only one terminal child, make the terminal the label of the current child. So this has happened here. Plus, we'll replace the E here. Okay? Star will replace the E here. And then there's many customized rules. So for instance, brackets don't add a lot of information. So we want to completely remove that tree. And what we get after this operation is this tree, which you probably have seen before in your data structures module, right? And this is something you probably already know how to evaluate. A depth-first traversal will be very easy to write to produce the value of this expression, right? And the result of this analysis phase, we call it syntactic analysis, and more detail will be given next time, is what we want out of it is the abstract syntax tree, the AST, right? So first, by analysis, we produce a parse tree, but then we want to convert the parse tree into an abstract syntax tree, which is much leaner. Much of the clutter is removed. It does have the correct structure of the expression, okay? And it's what is really useful out of this language recognition exercise. Is this clear? All right. So, what are grammars good for, right? What have we learned so far? So what we can actually do is language generation. We don't quite know yet how to do language recognition, right? But we're going to see how that works later, right? When we will be able to convert grammars into acceptors. And this process is called syntactic analysis, which is part of every compiler and interpreter, right? So the first thing is take the text of the program, convert it into an abstract syntax tree. And on that abstract syntax tree, perform interpretation or compilation. And I can't remember whether I discussed the compilers and interpreters. So a compiler has three phases, right? Has syntactic analysis, produces an AST. The AST is then converted into intermediate code that can be optimized. And then the optimized intermediate code goes to code generation, and machine code is generated. So it has these three phases. So the grammars will facilitate the first phase, which is called syntactic analysis. Okay. Now, big problem, ambiguity. All right? So if we look at the grammar that we have already defined, and at one of the expressions that we, or this is a simpler expression, right? We'll see that the parse tree is not unique. We can easily build two distinct parse trees for the same expression. And if we build the corresponding ASTs, we can see that the two ASTs capture different structure about the expression. And one of them is undesirable, which is that. Which one is undesirable? There's one we don't like. When you say like this, on my screen it's like this, right? You don't like the right one, right? Okay, so yes, the right one does not capture the correct precedence of the expression, but can be avoided, right? It's ambiguous. It has to do with too much recursion. There's an E here, and an E here, and an E here, and an E here. Too much recursion. Okay, so we would like the grammar to be unambiguous. We would like it to capture the correct precedence of operators. Is this clear? Okay. So this pretty much states the obvious, right? So we could correct the wrong precedence. We could find ways. But if we can get it right from the first time, why bother to correct it later, right? We might as well try to get it right from the first time. Also, non-ambiguous grammars will lead to more efficient parsing. Parsing is a very hairy subject. It would take 75% of a compiler's time in the first generation of compilers. Right? Newer compilers perform a lot more optimization, so the proportions of how the time is spent in the different phases of the compiler has changed a bit. But still, parsing is a serious effort. So efficient parsing is quite important. And we would like to have linear parsing, right? The parsing time should be linear in the size of the program. Right, and nowadays we get almost linear algorithms, right? And that cannot be achieved with ambiguous grammars. So we can't have ambiguous grammars expect efficient parsing. So before we go into how to avoid ambiguity, which is just a different way of writing the grammar, right? Let's talk first about the Backus-Nauer form. This is a syntax for defining grammars, right? So it's a language for a specification that generates languages. It's a meta language, right? It's a language for defining grammars, but grammars define languages. So Backus-Nauer form is a meta language. Let's look at a grammar in the form that we've been used to already. This is what we call the original grammar. And the equivalent BNF is useful because it allows a more compact expression of this grammar. What's new here? Well, our non-terminals will be anything in angle brackets. Right, so this is a non-terminal, and this is the same non-terminal. And in angle brackets, I can put anything I want, any characters, any digits, anything. Then we want to have a bit of factorization, so we use this choice operator. All right, so these are BNF meta symbols. The angle brackets, the arrow is replaced by this. Right, the bar represents choice. We have choice at the rule level. The square bracket represents factorization. Terminals will be enclosed in either single quotes or double quotes. Okay, so these are meta symbols. And the plus denotes repetition, iteration. The plus that appears here. Okay, so these are meta symbols. And let's see the correspondence. Right, non-terminals are enclosed in angle brackets. Terminals are enclosed in simple or double quotes. Our choice. And this makes it easy to use quotes as terminals. If I want to use single quote as a terminal, I put it in double quotes. If I want to use double quote as terminal, I put it in single quotes. Okay? So it works well. The arrow is changed into, because you can't type the arrow, and the BNF is supposed to be typable from a keyboard, right? So we change the arrow into double colon equal. Then we are allowed to group rules. We use the bar to group the body of several rules, and we use choice to represent either or, right, which allows factorization. So inside a rule, we can open a square bracket and put several choices of terminals in there. And we have this symbol that denotes one or more repetitions. And because of that, we can completely do away with one non-terminal. The D non-terminal essentially disappears. Right? So this is a much more compact way of specifying grammars, the backwards-now form. Is this clear? It's just syntax, right? And in fact is not that useful. So it appears in all the textbooks. But it's often used as a standard for specifying grammars of languages. So if you read the grammar of Java, which is available on the web in a publication, you will see it in backwards-now form. All right, and there's an alternative symbol, which is star, to denote 0 or more repetitions of something. Instead of plus, one could use star when it is meant to have 0 or more repetitions. So now let's, in backwards-now form, let's have a non-ambiguous grammar for expressions, all right, which is this one. You see, it's much more complicated. It doesn't use that much recursion anymore. Okay, so let's try to understand how this works. So an expression is sub-expression followed by term. And the sub-expression is sub-expression term plus, right? So notice the following thing. Whenever we have, let's say, I'm changing the non-terminals to these identifiers, A, B, C, D, just to make things simpler. So if I have A plus B plus C, because of this rule, I can only split the input into this part. I'm sorry, actually, that's wrong. Into this part and this part, right? This is going to be a term, and this is going to be a sub-expression. And because of that, the associativity of plus is going to be correctly handled. Then recursively, this sub-expression will be converted into another sub-expression and another term and a plus, right? Look at the definition of sub-expression. It's sub-expression, term, plus minus, right? And the next one, this is the empty symbol. Empty symbol can be anywhere between two terminals, all right? So recursively, I'm going to have a plus, a term, and the empty symbol as a sub-expression. So using only left recursion, so left recursion means that the recursion appears at the left of the body of the rule, will enforce left associativity on an operator. And that corresponds to what we know from practice. Plus and minus are left associative. If I perform A plus B plus C, I should first perform the A plus B and then do a plus C, which means that the abstract syntax tree should be like this: A plus B plus C, and not plus A plus B C, right? So this is wrong. If I had used right associativity, I would have enforced. Sorry, if I had used right recursion, I would have enforced right associativity. Okay? Now, notice that the star and division do not appear in the same rule. they appear in a lower level rule. This will enforce higher precedence for star and division, for multiplication and division. Okay? So if I have A plus B star C, right, I will see this as a term and this as a sub-expression, right? And when I see this as a term, right, when I see this as a term, you see that term is subterm factor. So this is going to be, let's say, this is going to be sub-expression, this is term, and here this is going to be a factor, and this is going to be a subterm. Right, so this will enforce this kind of syntax tree, star BC, which gives the correct precedence of higher precedence to multiplication than to addition. And then we have the power operator, and we would like the power operator to have even higher precedence than star, right? So we do that by having factor at even lower level than plus, right? So this operator appears here, and only inside factor can we have the power operator. Now the power operator should be what kind of associativity? Should have what kind of associativity? If I see 3 to the power of 4 to the power of 5, how do we perform this operation? Or this sequence of operations. What do we do here? What do we do first? 3 to the power of 4 or 4 to the power of 5? Louder. 4 to the power of 5, right? So it's right associative. It's no longer left associative. So notice that we achieve this by right recursion. Right? So the subgrammar for power expressions has right recursion enforcing right associativity, as opposed to the subgrammars for multiplication and addition, which have left associativity, right? So let's emphasize that, right? So here, this is the non-terminal, and this is the right recursive call, and in contrast, for multiplication, this is the subgrammar, and this is the left recursive call. Okay? Now, this kind of grammar will lead to a lot more complicated derivations, right? Why? Because if I need to, a single number should be an expression, right? So it should be in the language. But notice the derivation. From expression, I have to go to term and sub-expression, which will go to empty. Term should go to subterm and factor, which should go to empty. And factor should go to base, and the rest expression, this one should go to empty, and this should go to A. A alone should be an expression, right? So just for one symbol in one string that is made up of one symbol in my language, I should get a very complicated tree. So, alright, so remember, empty angle brackets are the empty string. And then there's another thing another choice that we might have made, right? We might have written this rule like this, because it's sub-expression term plus minus or nothing, which is 0 or more repetitions of that, right? I could have written it like this. If we do, we lose the associativity information. We don't know whether this rule should be left recursive or right recursive. Either could work. I could convert it into a left recursive rule, I could convert it into a right recursive rule. The language would be the same, but at that point I would not know the associativity. Okay? So there is structure in the language that I want to capture by means of the grammar, and it's important. So now if we take this expression, and this is given to you as an example, I'm not going to go through it in detail because I don't have the time, but this is the expression, this is the derivation tree. Okay? And you can follow it level by level. This is the frontier. Notice that the frontier has many instances of the empty symbol, which doesn't count. Right? So we start from here, empty doesn't count. I see an A. Then I see another empty symbol doesn't count, minus another empty symbol, B. Oops. Minus another B, empty symbol, star, right? So if you follow the frontier, then you get the expression. It's just to show that parse trees can be very complicated. And you can see the correspondence, right? I mean, like, you look carefully at it offline, and you can see that it is correct, and you can see how every derivation is performed, right? Which rule is applied at each level, right? So you can see rules being applied, and so on and so forth. And the important thing is to obtain an AST now. So we're going to perform a variety of simplifying operations, hoisting terminals to their parent nodes or even ancestor nodes. And what we get is this, which is what you would expect. Right? And if you look carefully, you can sort of see the correspondence between the AST and the parse tree, just that the AST is much simpler and it begs to be evaluated, right? Whereas with the parse tree, you don't quite know what to do. You would probably need to inspect it very carefully to make sure that it's correct, and you won't know. You won't even know. You will have to think a bit how to convert it into an AST. What is the rule for every node that you have to apply? But nevertheless, be assured that it can be done systematically. Is this clear? Okay. So, what have we learned? There are many grammars for the same language, right? And only some are useful. Most of them are not useful. Parsing is the process of building an AST. Eventually, that's what we're after, for a given string, provided that the string is in the language of that grammar. We want unambiguous grammars, and moreover, we want to capture structural properties of the language in the grammar, right? Associativity is one thing. Later, we're going to see nesting of blocks is another thing that we want. The AST can be built from the parse tree through an algorithmic process, though it's a lot of heuristics in it. So, but for every grammar, you will find the way, right? So given a grammar, there's always a way. You can't say in advance for any grammar how you would build the AST, but given one grammar, you would sort of, you would absolutely be able to derive an algorithm that changes the parse tree into an AST. Right, so to obtain an AST, the rule of thumb is that every tree segment is processed in a systematic way. So you would perform a depth-first traversal, and at every node you look several levels down and decide on how to convert. Right, and you typically do it post-order, so you do it from grounds up. All right, now, another important thing is stratification. So we've gone from expression down to digits. But this is not what happens in general. Compilers and interpreters use a stratified approach, two levels of grammars. For instance, every sequence of digits would be first recognized as a number, and every sequence of characters between double quotes would be recognized as a string, and then These entities, number, string, delimiter, keyword, all these strings are the terminals of a higher order language. So we use a two-layer approach, right? The low-level grammars, we would have a grammar for every lexical unit, right? Lexical units would be numbers, strings, keywords, parentheses, delimiters, punctuation, and so on, right? So each will form its own separate language, and for each we will have a grammar that has its own start non-terminal. These start non-terminals become the terminals of a higher level grammar, which performs syntactic analysis. So we distinguish between two levels, lexical analysis and syntactic analysis. Lexical analysis uses these multiple languages to create a stream of lexemes. So the stream of characters coming from your text, from the program's text, right, where the word while is actually a substring of 5 characters, right, it is converted into a stream of lexemes where every lexical unit is one entity, is one element of a stream, right? The keyword while is one element. The number 13 is another element. The plus equal operator is another element, right? It is not seen as individual characters anymore, but as one element. And we're going to focus in what follows, in the remainder of this lecture, on these low-level grammars, which are simpler. They're called regular grammars, and they're simpler. They have very straightforward recognition mechanisms, and that's the focus for the remainder of the lecture. So, lexical analysis grammars. Several, right? We have one for positive integers, and now the grammar and the non-terminals have sort of the role of procedures, and we can factorize grammars, right? So positive integer is a digit or a digit followed by another positive integer, where a digit is 0 or 1 or and so on and so forth up to 9. A string is double quote followed by a sequence of characters followed by double quote, where a sequence of characters is any of the printable characters, any of them, right? All the ASCII set, printable subset of the ASCII characters followed by another sequence, right? So this is how we define repetition. Or the empty string, because a string can be empty, right? Between the first double quote and the second double quote, we may not have any character. Identifier is an alphanumeric character followed by a sequence of an alphabetic character, followed by an alphanumeric sequence, right? Alphabetic is all the small letters, all the capital letters, capitals, right? And well, this is not really a letter, not alphabetic really, but we have to put it somewhere, so we choose to put it there, right? The underscore. An alphanumeric is either alphabetic or a digit. So you see here that we're reusing an entire grammar. The grammar of digits is reused, factorized, sort of used as a procedure. An alphanumeric sequence is alphanumeric followed by alphanumeric sequence or the empty symbol. So here we defined several grammars, in fact, a grammar for positive integers, a grammar for strings, a grammar for identifiers, and in the process, right, because of the need for factorization, we define several subgrammars that happen to be useful. The grammar of digits, the grammar of sequences of characters, the grammar of alphabetic characters, and so on. Is this clear? But we want these as separate entities. And when we read from the text of the input, we want the text of the input to be converted into lexemes, which are substrings that are elements of this language, right? So the stream of lexemes, one element will be the positive integer. It may have, later as a pointer, 10 characters here, digits, right? 2, 3, 4, 5, blah, blah, blah. And the next element is going to be an identifier, maybe. Right? And the entire identifier is in fact a string of 20 letters. But it appears as one element to the next level. And this simplifies the design of the next level greatly and creates a layer of abstraction that separates, from a software engineering perspective, is a very good thing, right? Separates the development into two separate modules that can be handled by different people, can be maintained separately, and so on. Notice that all of them are right recursive. There's only right recursion. Nothing else but right recursion. So these are regular languages. All right, when they're right recursion. Actually, this is oversimplification because we're not looking at mutual recursion, right? We're going to do that on the next slide. The fact that we're using right recursion, well, we could have used left recursion. We definitely don't allow middle recursion. All right, so that's what we want to avoid. And actually even can mix right recursion and left recursion. We can't allow middle recursion. Where was middle recursion previously useful? Can you recognize in this grammar, where is middle recursion useful? Louder. Base, very good, right? So expression, all these rules are mutually recursive. Expression appears in the middle, in between the brackets. And because of that, the number of open brackets must match the number of closed brackets. This is what enforces it. If my rule is either left recursive or right recursive, I will not be able to match open brackets with closed brackets. I will not be able to create a language where I enforce the bracket matching. All right? So that's a specific feature of regular languages. They are narrower, they are less powerful. But the advantage on the other side is efficiency. They can be recognized efficiently. All right. So this is what we do. We restrict all the rules to be of this form. Actually, we're even tighter in our specification. The rules can be only of this form. B goes to single terminal. B goes to terminal, non-terminal. So the non-terminal appears only at the end of a rule. Or non-terminal goes to epsilon. So that's a right regular grammar. The grammar that we've seen on the previous slide can be converted into one that looks like this. So it has the same power, right? And intuitively, that's what you have to remember, that there's no middle recursion. Right? It's only left or right recursion, even in the case of mutual recursion. Because what we want to avoid is this bracketing feature, which is very important, right? You wouldn't be able to have blocks with open brace, closed brace. You wouldn't be able to have brackets. It's a very important feature of the previous kind of grammars, which next time we're going to see are called context-free grammars and are surely more powerful than regular languages. Right, so I'm just giving one definition for right regular grammar, and we're going to see why in a minute, why I focus on this. Now, the way of recognizing regular languages is by means of deterministic finite automata, which we have brushed against last time, just as an example of using the switch case statement in C. But now we're going to learn what they are useful for. So the mechanism works as follows, right? It has a bunch of states, and it has a bunch of transitions, which are, it's essentially a graph, right? So the nodes are states, the arrows are transitions. The arrows are labeled by symbols. And what we want is to start in an initial state, and we have an input string. The input string initially has a pointer on the current symbol, initially at the beginning of the symbol. So the current symbol and the current state will give us the next state, right? So I look at the current state, I look at the current symbol, and I look where on my transitions from the current state does that symbol reside, and I'm going to take that transition. And in the process of transition, the pointer moves from the current character to the next character. And then the process repeats. And as it repeats, the pointer moves further into the string until it reaches the end of the string, possibly. Right? If the automaton has managed to move the pointer to the end of the string, and at that point it has reached a final state, which is the state with double circles here, and it's not necessarily unique. We may have more than one final state. But if we have reached a final state, at the end of the string is accepted. If we reach the automaton reaches the end of the string, and we are not in the final state, rejected. If in the middle of the string, right, from the current state, there is no transition labeled with the current input symbol, rejected as well, right? So the automaton accepts or rejects a string. So it's a language acceptor. It's a string acceptor. And it's the preferred way of implementing lexical analyzers. And guess what? So this is a little animation, right? So we move from the current state. The first symbol is 0. We take the transition that has 0 on the label, and we move on, and then we stay there till the end. All right. So it's the preferred way of implementing lexical analyzers, and the power of DFAs is the same as the power of regular grammars, right? The language generated by a regular grammar, I can find a DFA that accepts it, and vice versa. The language accepted by a DFA, I can find a grammar that generates it. All right? So this is the equivalent regular grammar, and notice how it works, right? State. So this state, I create a non-terminal out of it. All these are transitions to state 2. All these are transitions to state 1, right? 1, there is a transition to state 2, so all these are symbols on the transition to state 2. And state 2 has another transition to itself on these labels, and it's also a final state, so it generates the empty string. And this it complies with the definition of right regular languages, regular grammars, right? So if you go back to the slide where we defined right regular grammars, it's exactly in line with it. And this is why the power is the same. From a DFA, I can immediately generate a regular grammar, so they have the same power. Okay, another aspect here is that we want to factorize, we want to group together automata. So what we're going to do here is try to accept numeric constants, and we have several types. There's definitely integers, positive or negative. Then we have fixed point constants and floating point constants. Fixed point constants would be of the type 1.2, and floating point constants would be of the type plus minus in front, 1.2 e2 plus 3, right? And of course, we accept dot 3 as a fixed point constant, or 4 point instead of 4.0, right? So what we do is come up with an automaton, have several final states, but each final state has a different type specifier. So depending on which final state we have arrived at, we're going to decide the current string is either an integer or a fixed point constant or a floating point constant. Right, so we start in state 0. Let's assume that the input string is this. Right, so we perform transitions. On minus, we go to state 1. On a digit, we go to state 2. Right, had the string finished here, we would recognize an integer, right? But the string is not finished. So on decimal point, we go to state 3. Had the string finished here, we would have recognized a fixed point constant, right? But it doesn't, so we stay in state 3 for another symbol. And again, if the string had finished here, we would still recognize the fixed point constant. Then we see the letter E, then there's a plus, then there's 3, and the string ends here, and we recognize a floating point constant. Right, so we attach a lexeme type to every final state, and then we use that for a more sophisticated kind of recognition, right? And what happens if this appears in a long text input file? Well, the recognition is greedy. In that case, we will stop on the first symbol where we can't perform a transition, and if we are at the final state, however much we have managed to eat up, consume from the input, we will recognize that as a lexeme. All right, so when you have a stream of lexeme into a text file, the stop, there's no end of string, right? Well, there will be one eventually, but there's no, after my current lexeme, there's no end of string, right? So we're going to stop on the first symbol on which there's no transition. And if we are at a final state, then we can recognize one lexeme. Is this clear? So, what have we learned? DFAs are essentially graphs, nodes are states, arcs are transitions. There's an input tape. It goes back to, the concept goes back to the time when tape recorders were in fashion, right? So there's this correspondence between the current symbol and the current place of a head on the tape, and then the tape moves and moves on to the next symbol. A transition is performed only if the current state has an outgoing arrow labeled with the current symbol, right? If we've seen that. And the result is a new state, right? And the head moves to the new symbol, and the machine is ready for yet another transition after that, right? We have rejection when we don't have a transition on the current symbol, and when we finish the string but we are not at a final state. Otherwise, we recognize, and the final state will give a type to the current lexeme. Or token. You also see under the name token. And a lexical analyzer is also called a tokenizer. All right. Regular expressions. So, regular grammars, DFAs, and yet another way of specifying and recognizing the same type of languages is regular expressions. It's a language that defines other languages, right? So it's a meta-language. There's a formal definition. I'm going to skip this. All right, I'm going to move on directly to Ruby. Right, so the language Ruby is one of the few that has regular expressions as first-class objects. First-class object is something that can be assigned to a variable and can be an argument to a function. Right? And we want to practice regular expressions, so that's why we use it for. So we're not going to have a full introduction into Ruby today, just enough information to be able to practice regular expressions. And I have, so when you run the interactive interpreter for Ruby, you get this kind of a prompt. The syntax of a regular expression is a string between slashes, forward slashes. So for instance, if I say A plus B, this means at least one repetition of A followed by a B, right? And this is an object. So when we evaluate it, it just replies back the same value, right? It's the kind of language that is an evaluator. So 2 plus 3 will return 5. Now, A plus B is an object. So now, I can, from inside the object, I can select the method that performs matching. And I can match it with some string. And I'm going to have 1 3 A's, B and 2, and the result is an object of type, you would expect a string, but it's an object of type match data, and inside you see the substring, the longest substring that matches my regular expression. So A plus B is at least one repetition of A, but as many as I want, more than one, and followed by a B. So I can turn this, because it's a programming language and I might want the string, I can turn this into a string using the method toS. So I get the string. So now we can practice, right? For instance, if I say 1, 2 in square brackets means choice between 1 and 2. So my strings are either 1B or 2B, right? So if I do this, I'm going to get the empty string because there's no match. However, if I put a B here, I'm going to get 1B. Right? And it can get as complicated as you want inside here. So another thing that it can do is A followed by B star, all followed by C plus. So can you tell me here a matching string? Let's say we leave the 1 and 2 just for kicks, and tell me in between 1 and 2 a string that would match that regular expression. So how about AAC? Would that work? Yes, it should, right? AACBC. Right? So it's A star means as many A's as I want, but I needed the C, and I need at least one repetition, and then I do it again. I get to do it again. Okay? So that will be a very nice way for you to practice. And in fact, there is this site called regular.com. That is made using Ruby, and you can practice on the web without installing your interpreter. So you see the slash is already typed for you. So here you can say A plus BC, for instance, and you want to say the testing string, and we're going to say the 1 again just to show that what we match is a substring, AAABC, and 2. And then we get the string where the matching part is highlighted. Okay? And if I say here, instead of B, I say D, I will have no matches. Okay? So you can go to the site and practice on your own. And let's go through the syntax. So the empty string is empty brackets. Bar represents alternatives. We have already seen that A bar B is either A or B. Square brackets is one symbol alternatives. Star is 0 or more repetitions of the preceding, and you can use brackets for grouping, and you can apply it to a bracket. And then we have a shortcut. All the other symbols are not essential. So plus is 1 or more repetition of the preceding, right? I can always replace A plus by what? Louder. A plus replaced by AA star. Very good. Or A star A, right? Same thing. Question mark. So if I say a question mark is 0 or 1, 0 or 1 occurrences of that. I can replace a question mark by, louder, louder, a or empty, very good, right? So a or empty would be a question mark. MN, right? So if I say a to 5, it means between 2 and 5 A's. So we can replace this by louder. Yeah, so that would be one way. So you can say AA or AAA or AAAA or A. I should have chosen 2, 3, right? AAA. But it's probably easier to say A, empty, A, right? So we can factorize. And we can factorize to the left or to the right. So brackets allow grouping. Now, if any of these symbols, you want to use them as terminals of the regular expression, right, you have to escape them. You have to put a backslash in front. And of course, backslash would be double backslash. Now we have macros. So macros backslash D, it means a digit character, same as 09. So it's a shortcut. Backslash D, backslash capital D is a non-digit character. And one interesting thing that I forgot to put here is that if you put a caret inside the square bracket, it means exclusion. It means none of the characters that are included. And also, you can use a range between 0 and 9, and the range is taken in the order of the ASCII characters, right? So because between the ASCII code of 0 up to the ASCII code of 9. Backslash W is a word character, so the alphanumeric ones, and backslash capital W is a non-word character. So all those characters excluded. All right, so we're going to play with this a bit more, right? This is a range specifier, exclusion operator. Multiple ranges can be placed inside, and we've seen the usage, right? And you can go to more complicated expressions, and remember, right, we're going to talk more about object-oriented languages, but those of you who have done Java would know that x.something selects something from inside the object. The important thing is that a variable can be assigned a regular expression, one of the few languages where this can happen. And we have a matching method for regular expression. And we typically want the string, so we use the 2s method. So, hopefully you remember what you have learned. Time is, it's a bit late, so I'm going to skip this. And, right, what have we learned? Grammars, DFAs, regular expressions, right? Next time we talk about analysis, so we're going to talk about context-free grammars, which are slightly more sophisticated, and how to recognize languages specified by those grammars, how to turn the grammar into a recognizer. So this is it for today. If you have any questions, I'm going to take them outside because I think there's another class coming up, and I don't want to inconvenience them. So thanks for your patience. See you next time.